Right, hi folks, this is Larry Maslino. I wanted to record a short video to help you get started in the Module 3 MyLab's homework. And this homework is going to have to do with finding instantaneous rates of change. And so the idea will be to find the derivative function and then evaluate the derivative function at a certain x value. For example, just to give you a little background, let's say we have some kind of a function that maybe looks something like this. We'd like to find the instantaneous rate of change at a certain x value. Let's say x equals 5. Well, really what that represents is the slope of the tangent line. So if I was to draw this blue line that's tangent, the slope of this tangent line is the instantaneous rate of change. So instantaneous rate of change is the same as the slope of the tangent line. And to find that, we can use the derivative function. So we could take the derivative and evaluate it at the x value we're interested in. If we're interested here, x equals 5, we could plug in x equals 5. What if you wanted to find the slope of the tangent line over here somewhere? This tangent line. And this is at x equals 9, let's say. Well, you would work out f prime of 9. That would give you the slope of this green tangent line. All right, so you're going to be doing that here in this homework. And now, remember that instantaneous rate of change is different than the average rate of change. The average rate of change is not a tangent line. The average rate of change is the secant line. So this is the slope of a secant line. So keep in mind this distinction. All right, well, let's go ahead and get started with this one. So it says a body moves on a line and its position, I'll write it as s of t. This position function is t squared minus 4t plus 3. And it's over the time interval from t equals 0 to t equals 5. All right, let's go to the first question. It says, what's the body's displacement? Well, displacement is really change in position. So what they're really asking me to calculate here is, what is the position at t equals 5? What is the position at t equals 0? And find the change. So think of it as taking s of 5 subtract s of 0. Well, I could just use this displacement function. So s of 5 is going to be 5 squared minus 4 times 5 plus 3. And then back here, I'll put s of 0. That's 0 squared minus 4 times 0 plus 3. All right, I'll just work this out. In this first parenthesis, we've got 25 minus 20 plus 3. In this back parenthesis, 0 minus 0 plus 3. This is 8 minus 3, so we're getting 5. So the displacement is 5, and we're really measuring in meters, so 5 meters. All right, let's go to the next part. It says, what's the average velocity? Well, average velocity, you can really think of as displacement over time. So the displacement was 5 meters. The time duration here was 5 seconds. So this is going to be 1 meter per second is the average velocity. All right, let's go to the next part. It says, what is the body's speed at the left and right endpoints? Well, really, that means that t equals 0 and t equals 5. Those are the left and right endpoints. Now, speed, when they say speed, they really mean the absolute value of the velocity. So speed is velocity, but without the sign attached to it. But if we want to figure out velocity, what we're going to need is the derivative. So velocity is the derivative of this position function, s prime of t. We can write it. All right, well, we're going to use the limit definition for derivatives. So it says the limit, I'm going to use delta t here, as delta t goes to 0, and we're going to want to calculate s of t plus delta t minus s of t all over delta t. This is the limit definition from back in Module 2. All right, well, how are we going to figure out S of t plus delta t? Well, remember, S of t is t squared minus 4t plus 3. So I'm going to be plugging in this input t plus delta t in for t. So this is going to be the limit as delta t goes to 0. All right, I'm going to plug in t plus delta t squared minus 4t plus delta t plus 3. Okay, that's this first part of the numerator. All right, now I'm going to subtract this S of t. Well, that's subtracting the original displacement vector, which is t squared minus 4t plus 3. And this is all over delta t. So what I'm going to try to do here is simplify the numerator. I'm going to try to cancel out the delta t on the bottom, then take the limit. All right, so let's write this out. This is the limit as delta t goes to 0. All right. How about t plus delta t, that parenthesis squared? Well, that's going to be t squared plus 2t delta t plus delta t squared. All right, here it's going to be minus 4t minus 4 delta t plus 3. And this back red parenthesis, I'll just distribute the subtraction sign inside. So it's going to be minus t squared plus 4t minus 3 all over delta t. All right, let me try to cancel out some parts of the numerator here. It looks like we have a t squared and a negative and a minus t squared, so those cancel. Minus 4t plus 4t and plus 3 minus 3. All right, let's see what's left then. We have the limit as delta t goes to 0. 2t delta t plus delta t squared minus 4 delta t all over delta t. Well, remember, we want to cancel out that delta t in the denominator. So what I'm going to do in the numerator is factor out a delta t. If I do that, it's going to leave me 2t plus delta t minus 4 all over delta t. But now I can cancel out delta t top and bottom. Now I'm going to take the limit and let delta t go to 0. Well, if delta t goes to 0, this expression is going to 0. That leaves me the answer 2t minus 4. So after all this work, what we figured out is v of t is 2t minus 4. All right, well, they want us to find the body speed when t is 0. Well, v of 0 is 2 times 0 minus 4. That's negative 4. But speed is the absolute value of velocity, so the speed is really going to be 4. So that's the left end point, so this is when t equals 0. All right, how about when t equals 5 for the right end point? Well, we'll work out v of 5 then. That's 2 times 5 minus 4. That's 10 minus 4, that's 6. All right, how about the acceleration? Well, it turns out, let me write down that v of t is 2t minus 4. It turns out acceleration is the derivative of velocity. So remember, velocity is the derivative of the position function, and acceleration is the derivative of the velocity function. All right, so let's go ahead and set up the same kind of limit process. So this is going to be the limit as delta t goes to 0, v of t plus delta t minus v of t all over delta t. All right, to get started here, I'm going to plug in t plus delta t in this velocity function. So this is going to be the limit as delta t goes to 0. 2t plus delta t minus 4. All right, now in the back here, I'm going to subtract v of t. Well, that's just 2t minus 4, and this is all over delta t. All right, let's expand this. So this is 2t plus 2 delta t minus 4. Back here, I'm going to distribute the subtraction sign. So it's going to be minus 2t plus 4 all over delta t. All right, looks like here's a 2t, subtract 2t, so those cancel. Subtract 4, add 4, those cancel. So it looks like we have the limit as delta t goes to 0 of 2 delta t over delta t. Well, of course, these delta t's cancel. I'm ending up with just 2. So the acceleration here is equal to 2. And notice this doesn't depend on t. So what that means is the acceleration is constant. So the acceleration at t equals 0 is 2. The acceleration at t equals 5 is also 2. All right, when does the body change direction? Well, for that, we could set v of t equal to 0. That means 2t equals 4. That means t equals 2. Let me check that the velocity really does change sign before 2 and after 2. Before 2, so before t equal 2, I'll just pick, let's say t equal 1 as an example. v of 1 is 2 times 1 minus 4. That's a negative 2. Let's do a check after t equals 2. Let's say v of 3. That's 2 times 3 minus 4. That's positive 2. So yes, the velocity changes sign before 2 and after 2. So that means it does change direction at t equal 2. All right, so for this example, you had to be calculating the velocity function, which is the derivative of position, and then calculate the acceleration function, which is the derivative of the velocity function. All right, let's take a look at another example here. All right, this one says the area A is pi r squared of a circular oil spill, and it changes with the radius. At what rate does the area change with respect to the radius when the radius equals 10? So if you can imagine this oil spill over time, the oil spill is getting bigger and bigger, so the radius is getting bigger and bigger. But also that means the area is getting bigger. So these rates are related in that kind of way. So what they're asking us to find out is, at what rate does the area change with respect to radius? That is a derivative. Really, they're asking us for dA dr, the derivative function. The way I can work this out is take the limit as delta r goes to 0 of a of r plus delta r minus a of r over delta r. Right, so I can write this as a of r, the area function. All right, let's plug in. So this is going to be the limit as delta r goes to 0, pi. All right, now I got to plug this in for r. So it's going to be pi r plus delta r squared minus, now we need just a of r back here. That's just pi r squared all over delta r. All right, let me expand this parenthesis. So it's r squared plus 2r delta r plus delta r squared minus pi r squared. All right, let me multiply this pi inside the parenthesis here. So it's going to be limit as delta r goes to 0 of pi r squared plus 2r pi delta r plus delta r squared minus pi r squared all over delta r. Well, I am noticing something can cancel out here. We got a pi r squared minus pi r squared, so those cancel. On the top, let me factor out a delta r. So I'm going to have a limit as delta r goes to 0. I'm factoring out a delta r on the top. So that's going to leave me 2 pi r plus delta r all over delta r. But of course, delta r cancels top and bottom. When I go to take the limit as delta r goes to 0, this expression here goes to 0. So it looks like I'm just left with dA dr is equal to just 2 pi r. All right, but they're asking us evaluate dA dr when r equals 10. So this is just going to be 2 times pi times 10. So 20 pi is the answer they're looking for here. So the answer here is 20 pi. Okay, folks, hope this is helpful as you are getting started here in this Module 3 homework.